So hello guys, so today we are going to discuss about designing of gates for transient analysis. So this becomes very important part of the CMOS VLSI design. So for any combination circuits or for any gates that we are going to design and do the transient analysis, we require a reference. So we take the reference from the inverter. We all know the inverter has a simple structure having just one NMOS, one PMOS. This is a VDD, this is a VSS, this is the V in, and from here we are going to take the V out. And for that we know that it is having the beta parameter as BP, the beta P, and also having the width of WP, and it is having the beta parameter of beta N and width of WN. So whatever the circuits that we are going to design, it must be related to these WP and WN. So by considering these parameters of WP and WN, we are going to design some of the gates that are required. So now we are going to design about 2 input NAND gate. So 2 input NAND gate is given by y is equal to a dot b whole bar. So we know that whenever there is a dot, the NMOS will be in series and PMOS will be in parallel. Let's do the circuit. These are the PMOSs. Here comes the V out, and this is VSS. This is the general AND gate we are going to design. So first let us take designing for the normal rise time. If you consider the rise time, then we need to consider the path from VDD to V out, where the P tree comes into picture. The P tree for this NAND gate is given by, here comes VDD, this is RP, this is RP. Say both the MOSes are identical, and here comes VDD. For the worst case, we cannot consider both of the RP at the same time, because we know that whenever the two resistors are in parallel, the net resistance would be halved. So we are going to not consider both the resistors at the same time. So for the worst case, we're just going to consider any one of the RP. So I'm going to consider this RP. This is V out. This is VDD. This is RP. So now we are going to compare this worst case scenario of rise time with the normal inverter. We also know that, let me draw the normal inverter over here. Okay, so it is having WN, WP, WN over here. So we are going to compare the P tree of the inverter with this P tree of the AND gate. So we know that the inverter is having only one PMOS, so this gonna be also one PMOS. This is a reference inverter. So for to differentiate both of them, let me name it as RPN, which means RP of NAND gate. Okay, let's do the analysis. Say both of them are equal, then we get RPN is equal to RP. So we know that the formula of RP is given by 1 divided by beta Pn times of VTD minus mod of VTP is equal to 1 divided by beta P times of VDD minus mod of VTP. Let us consider both the both the cases, that is in NAND gate and in the inverter. Both are operated at same VDD and both are having same thresholds. Then both these conditions get cancelled. So we are left with beta P is equal to beta Pn, or say WP by LP Kn dash is equal to Kn dash WPN divided by LPN. So both these get cancels, LP also get cancels. So what we are left, WPN is equal to WP. So whatever the width of the normal inverter is there, this can be considered for the NAND gate also, WP and WP. Now let us do it for the fall time. So for the fall time, let us consider the worst case here. For discharging of this Cout capacitance, both the conditions A, B must be on. So what will be the worst case? VSS, RN, RN, Vout. So this is RN capital N, RN capital N. So now we're going to compare this entry of NAND gate with the reference inverter. The reference inverter also have just one NMOS. So let be this RN. This is Vout. So now here we get to see that 2 RNN is equal to 1 RN. What we can say is 2 RNN is equal to RN. So if we write the expression for the RN, we get to see that beta N capital N VDD minus VTN is equal to 1 divided by beta N VDD minus VTN. Say suppose these both are operated at the same VDD and having same thresholds, then both these get cancels. So we get that beta N capital N is equal to 2 beta N. If you substitute the value of the beta, that as Kn dash W by L of N, then we get to see that WNN of N is equal to 2 times of Wn. This is the required condition for the entry. So whatever the width of these two NMOSes are there, they must be equal to 2 times that of the width of the normal inverter. So then this would be 2 times of Wn. So I hope you got the clear picture understanding of this designing of gates for transient analysis. This was just for the NAND gate, and in further videos we'll try to consider more complex circuits. Till then, thank you.